repeat some stuff that Shehan said, maybe prove a couple of theorems that Khan mentioned combinatorially, that I asked if they can be like proven combinatorially. It was a trick question, I knew the proofs, but maybe you should see them as well. And I will talk about where I want to go with my set of lectures, okay? So I will start with the definition of a partition once again, but I want to mention a couple more things. So let pi, which is lambda 1, lambda 2, lambda 3, a finite list of positive integers in non-increasing order, so that we pick one order. We call this pi a partition. Then pi is called a partition. Right? I mean, Jan wrote some examples, so she went for 4, but she was writing it in like additive notation. I'm just writing it as a list. It's just easier for me. Here's the definition of partition. So I have positive integers, and they're in some order, but I pick non-increasing. So let's pick an example. For example, 5, 1, 1. That's just a partition. It's a finite list of positive integers in non-increasing order. So there can be some repetitions. It doesn't need to decrease, is what I mean. So there can be some repetitions. And here is a fancy one, the empty set. It's a finite list of 0 positive integers, which is also fine for us. Empty list is also a partition. Okay? Now let me define the size of a partition. So it's a finite list of positive things, so I might as well sum it up and see what the total is. And we define the size of pi to be the sum of all these lambda I from 1 to however many parts you have. But it's a finite list, so it must be finite, right? And this is called the size of pi. So this is the size of pi. So that now we can say, oh, we're partitioning this integer or that integer, so on and so forth. So 5, 1, 1, you add them up, it's a total of 7, so it's a partition of 7, right? So this is a partition of 7. And this empty list, it's already mentioned, it is the partition of 0. It is the conventional partition of 0. When you sum it up, there are no points, you just add 0, so it is the only partition of 0. Cool. So part that we pick non-increasing, so the first part is the largest part, right? And it has finitely many parts. We can just give some notation to that too, but maybe we can see it. L of pi, the largest part is lambda 1, and number of pi is the number of elements in pi. And these elements, we will call them the parts. So I will directly change it. It is the number of parts in pi. So lambda 1 is the largest part, lambda 2 is the second largest part, lambda 3 is the third largest part, so on and so forth. Right? Okay. And I want to say this, if this is for the future, if lambda, the index of lambda is an even number, like lambda of index 2i, I will call it an even indexed part. Even indexed part. Or if it's an odd number, for some I, whatever the I might be, that's an odd indexed part. That is for the future. That is, so lambda 1 is an odd index part, lambda 3 is an odd index part, lambda 2 is an even index part, so on and so forth. Right? Any questions about that? Just definitions so far? So this is a combinatorial object. We can list many of them. We can try to count them. We can just ask questions such as, how many partitions of 7 are there? Now it makes sense. Now we just say, oh, How many partitions of 7 are there? We take the 7. So we're looking at all the finite lists whose sum is making 7. Like the total sum becomes 7. I think there are 11 of them. We can list it though. The point is we can list it. However, like, you can run out of steam quite quickly. Like how many partitions of 20 are there? It just becomes quite huge. So you start with like, oh, I have one part like that is 20, just one chunk, fine. 19 and 1, good. 18, 1, 1, okay? 18 and 2. But then the list keeps on growing. In a sense, you really don't want to list them one by one at all times. You want to do some other things. And one trick is the generating functions. That's why we moved towards the generating functions and just went in that direction, right? But before I do that, let's still keep them as combinatorial objects one by one and look at their graphical description, right? The Ferris diagrams. So when you're given a partition, and I will take something like quite large, let's say I want to keep it, so 7, 6, 6, I don't know, 4, 4, 3, 2, 2, 1. It's a finite list of positive integers that are in a non-increasing order, right? The Ferris diagram is you take the largest part, you draw that many boxes in a row. So 7, I draw 7 boxes in a row. 1, 2, 3, 4, 5, 6, and 7. It worked perfectly. This time, it could have gone wrong. So 6, you draw a second row with 6 parts, 6 boxes to represent the parts. Then that, another 6. Then I need a 4, and 3, and 2, and 2, right? And 1, yes, thank you. So we can ask, what is this partitioning? What is this partitioning? What is the total size of this? So 13, 19, 23, 26, 30, 31. So the size of this, if I call this pi, is 31. Good. What is the largest part, we can ask? And the largest part is the first one. It is just 7, right? The number of parts. Now we have an explicit example, so we might as well just count it. So 3 parts, another 3 parts, 2 parts, 8 parts total. Number of parts of pi is 8. And they're all here. They're just like the first row is the largest part. The number of rows, the first column, is the number of parts. And the total number of boxes is the total sum anyway. Ooh. My microphone is not there anymore. Okay. Now what about this? We have this vague triangular shape that is a partition visually. What if I were to look at the column-wise? Because we made the choice. Like we started writing boxes in a row, but we could have put them in columns as well, right? What if I look at them column-wise? Would that also be a partition? So how many boxes are on the first column? I would say that 1, 2, 3, 4, 5, 6, 7, 8 boxes in the first column. Then the second column, it would be 7. Then it is a 5. Then it's a 4, 3, 3, and a 1. Cool. And let's give it a different name. So this is pi star. So would you believe me if I say that this has the same size as the original partition that we started with? It's the total number of boxes, right? I mean, I didn't add any new box. I just count them column-wise. So it actually would have the same size. Another thing that I didn't mention is that this is also a partition. This is also in non-increasing order. You see? So this was a partition. We looked at that column-wise. This is also a partition. And we said the total size is still the same. And what about the largest part? So the largest part now of this partition, just looking at the definition of it, is 8. It's the first element. Well, that was the number of parts of the last one. And the number of parts of this guy is 7, which is the largest part of the last one. So number of parts and the largest part switch places when we go from rows to columns. oh, this is the number of parts of this, and this is the largest part of the pi star. So this connection is called taking a conjugation of a partition, and these are called conjugate partitions. You look at your Ferris diagram, you draw your main diagonal, right? So you start with a partition, like here. You draw your Ferris diagram. You look at your main diagonal, starting from the top left corner. You flip it over that. You just flip it, so these boxes on the diagonal doesn't change places. You would get the Ferris diagram of the last guy. So that column would turn into that row. You would get the Ferris diagram of the conjugate partition. But what is more important maybe here is that in the conjugation, the total doesn't change, but the number of parts and the largest parts switch places. Good to know. Okay. So we're still getting our hands dirty. We're still keep playing with partitions one by one. But again, just as Jean did, just as Khan did later on, I don't want to deal with them one by one. I want to deal with them in bulk. So I will move towards an object that will do the counting for me. I'm not going to do this dirty work. So for that, I will define what a generating function is. So a generating function for me is given any sequence an of your interest, hopefully in integers from 0 to infinity. Given an a sequence, this sum of an q to the n is the generating function of an, that sequence. That is just an abstract way of writing it. That is actually just an enumerative way of writing it, I guess. That I'm just trying to say that you want to know the information about an, the sequence that you're interested in. You encode it in your list by just putting it in front of a term which is going to keep track of the index for you. So exponent of q is keeping the index of this an for me. Right? Whenever I see that q to the 50, I know I'm actually looking at the 50th term of that sequence. I will do things with that. When I need to, I will multiply things, or I will just split things. But it is going to change the series. It's going to do arithmetic in the series. But in the outcome, when I look at q to the 50, it is going to be the 50th term of the new thing that I'm looking at. So that is how we will use to generate more complicated examples from smaller examples. Cool. But when we talk about the generating functions, what are we actually doing? What have we did so far? So we took the partitions, we organized them with respect to their size, and we want to see those size appear as the coefficient of q to the power n. So I want to see the q to the power 5 to have the coefficient which is the number of partitions of 5, right? So in a really abstract way. So let me define two sets. Let P be the set of partitions, any partition. And let D be the set of partitions into distinct parts. So two definitions. Let P be the set of all the partitions. Let D be the set of all the partitions in distinct parts. What we want generating functions to do is that I want to take these partitions one by one from this set. Then I want to group them with respect to their sizes. Oh, thank you. You see? You take the partitions. You put the size of that on top of Q. So in an abstract sense, this is really what we're doing. We're writing the partition down, summing up its parts. It becomes the size. We tag it along as the exponent, and we count each and every one of them one time. So there's a 1. So you take that 5, 1, 1. In your huge sum of things, you take that 5, 1, 1, and say, oh yeah, this is just 5 plus 1 plus 1, so it becomes a q to the 7, and that is going to contribute to the coefficient of q to the 7. There are other q to the 7s here and there too. And after all, when you combine them all, you get the number of partitions of, this is lowercase, this is uppercase, the number of partitions of any n, or 7, with q to the n attached to that. And n starts from 0 all the way to infinity. Is that okay? So there's an abstract way of thinking that, there's an enumerative way of writing that, so that's how you group things. But the question becomes, and we addressed it a little bit, Jahan definitely addressed it quite a lot, like, what is that? It's just, like, this is abstract, this is enumerative. I still didn't say anything. I'm just like I'm just saying words, but there's no numbers going in. The same deal here too. So you can take partitions into distinct parts and group them with respect to their sizes. It's the abstract way of thinking what a generating function is. And you can just say P, D, the number of partitions into distinct parts. I will say this P sub D of Q and greater or equal than 0. Okay, cool. However, so far we don't have much machinery. I mean, actually we learned some machinery, but just to recall, what we can do to understand this generating function is we might as well just count these partitions, write them one by one, and actually do the calculations and write down what it should look like. So we can say, well, how can I make q to the power 0, the 1? There's only one partition of 0, which is the empty list. So there's just 1. Then how many partitions of 1 are there? So I'm literally writing it just as an open list. There's only one partition of 1, which is just 1. So it's the 1 that is kind of missing here to the power 1. There are 2 partitions of 2, which is a 2 and a 1 comma 1. So that's the 2 as the coefficient. So at least it's easy for now. 3 partitions of 3, 2, 1, full ones. Then 5 that Jan listed, I'm not going to list. So on and so forth. Okay, so it's a list. Abstractly, we're grouping things with respect to their sizes. We want to understand these numbers that appear as the coefficient. In reality, we don't have a good formula to calculate them. We definitely don't have a good formula for these coefficients. We already saw that. There's not an exact direct formula for these numbers. What we have is a formula for the total thing which helps us to calculate it. So we don't have a direct connection, but we have a secondary connection. We can write formulas for the generating functions. Same here, we could have done the same thing here as well. This would look at 1 plus q squared, this time just 1, because there's only one partition of 2 that is into distinct parts. 2 partitions of 3 into distinct parts, and for 4, I guess it's also 2. Q4. So the question would be like, what about the formula? Like formula, please. So that we can see like some other properties, we can maybe just manipulate things, right? So we already saw that there is a formula. It comes from the infinite product, right? And Jean already did that, so let's erase it and directly jump to that. And the formulas here are, which I can squeeze in, are as follows. This guy is 1 over q base q sub infinity, that Pochhammer symbol, and this distinct one is minus q is q sub infinity, where this a base q sub infinity is this infinite product I from 0 to infinity, where I have 1 minus a q to the I. So it's 1 minus a, 1 minus a cube, 1 minus a cube squared, so on and so forth. So we have these generating functions explicitly, we have their formulas as infinite products. Good. Well, but if you remember it, like we didn't start it like this generally. We didn't start with like, I mean, we can use any part. What if I want to bound like the part size that I can use? What if I want to bound the largest part? How about I change the problem just a tiny bit? Let Pn be the set of partitions with parts less than or equal to n. Maybe I should use capital N. Let Pn be that being n. What if I want to put an extra bound? What if I want to refine things, refine my understanding of how these things work? The same here too. I want dn, b sub n, to be the set of partitions into distinct parts where all the parts are less than or equal to n. So in an abstract sense, nothing changes. What I want to do is I will take all the partitions that I counted that are in this set, take them, group them with respect to their sizes. Here, things would change, but I don't know how it is. So what I would say is, yeah, I mean, I know that I'm supposed to, that these things are less than n. The parts are less than n. Whatever that might mean. Q to the n. So there's an extra bound on these things. It would change the numbers. And we actually saw how the formulas would change as well, right? Here, every parenthesis was given as one part size. So it was 1 minus q. Like the exponent of q, that parenthesis was giving you what part size you have. So when you have 1 minus q cubed, if 1 minus q cubed is what you're saying, you're talking about the part size being 3. If it is 1 minus q to the 50, you're talking about the part size 50. So if I have a bound on the part size, what this is going to change is this infinity. So I just need to make sure that I go all the way up to that size that I have. So these infinities will switch to n's. And that's all there is. And it makes sense, right? I mean, let's backtrack. If I have this finite version, where I have the bound on the size to be n, if I extend this bound, as n goes to infinity, this would go to that infinity. It's just, it goes to the infinite case too. Cool. Now, here's one more thing. So I said Pn be the set of partitions with all the parts being less than or equal to n. What if I define this different set, sub n of P, which is the set of partitions where the number of parts are less than or equal to n. What do you think the generating function of this is going to look like? So instead of bounding the largest part, now I want to bound the number of parts. It will be the same thing. Conjugation would say that, well, if you bounded this, it is the same as bounding the largest part for the conjugate part. So it will be the same thing, right? So it will be the same here. So technically, this is also the generating function for those guys, if you want to have it that way. But maybe we got to be careful. What if I have partitions into distinct parts and I bounded the largest part? I have a partition into distinct parts. Let's give the example 3 and a 1. So the partition that I have is 3, 1. If I were to conjugate this, I'm not in distinct parts anymore, right? The conjugate of that would be 2, 1, 1. So we can't always use this trick. It is not working at all times. However, for ordinary partitions, you can exchange a bound on the largest part and a bound on the number of parts, because it's just conjugation. Cool. So we understand what a generating function is fully. I will focus on the abstract sense, what we're doing later on. That's why I want to go in that direction. And we have some formulas as infinite products for these generating functions. But how does it all tie together? There's the partition, we're counting it. What are we doing to the Ferris diagram? In a sense, or can we visualize what we're doing in the Ferris diagram that carries the count of partitions in the generating functions. In a sense, what we're doing, how a Ferris diagram just plugs into the generating function is, you're just putting a Q in each and every box, and you just multiply them all together. So this, you put a Q in each and every box, you multiply them all together, it becomes Q to the 4th. That is the size that you have. That's the number of boxes, right? So that's how Ferris diagram kind of go into that. You can think of it that way. Okay. So we made some fashionable choices, but they were all choices. We put Q's. Q was the traditional variable. We could have put any name. We put size. It could have been some other statistic, which we shall see soon. We decided to count the number of all the partitions, number of partitions in the distinct parts, but we could have counted other sets of partitions. We plugged in Q's in these boxes and decided to multiply them all together. We could have put maybe different variables, which we will do. And with these different choices, we will have a more generalized, maybe a richer family of things. But before that, I also want to say that we have a product representation, fine, a formula, but this is not the only representation, for example. We came really close in Kahn's lecture that we can also write some representations for these generating functions. And any different representation for the generating function actually gives you some extra information. So maybe we should go towards that and just say, well, why don't we write an equivalent form of these as sums? And yeah, for that, let me remind you what Kahn proved. So one of them was the Q exponential theorem, right? Which is 1 over z q infinity. So it's an unbounded case, but we don't care. We can look at the bounded case later on if you want to. This is the sum z to the n divided by q, qn, and n goes 0 to infinity. Cool, we've already proved it using the analytic method. If I want to somehow relate this formula with the generating functions that I know, maybe I should plug in something for z. What do you think? So this looks like the first guy over here, right? The 1 over q sub infinity, the infinite version. Right? For that, I should plug in z to be q. So that formula already says that 1 over q infinity is the sum of qn divided by qn. Good. So we have a sum representation of this generating function that is, so levels of abstraction, the levels of just consideration. So here is this infinite product which we know as the generating function for the number of parts of any partition. And here's a sum representation of that. We already proved it analytically from that analytic side with a z. And now I just plugged in z being q. We just simplified it a little bit, but we got a sum representation. So one question might be, can we see that this is really the generating function for the partitions? Can I actually see and construct these partitions that I'm talking about? So I'm convinced it's not just an analytic formula, but I'm convinced that combinatorially, yes, this is the generating function for partitions. For that, let's give a combinatorial proof. So look at the inside of this. For a fixed n, this summand q to the n divided by qn is just one of the summands. I have a fixed n. This q to the n, I would say, is representing a partition, and maybe it is representing a partition of n boxes organized in a column. So this size, the total size here, is fixed to be exactly n. Is that okay? So I split one part of it. What is left? The other side of this thing is 1 over QQ sub n. What do you think this is? I mean, we already saw it like here. We already had some resemblance. This is the generating function of partitions into number of parts being less than or equal to 10. Or with the largest part being less than or equal to 10, or flip it, the number of parts being less than or equal to 10, right? So this is, we already know that this is the generating function for partitions where the number of parts is less than or equal to this small n here. So that portion would generate some partition, that vague triangular shape that we had, just as in the example above. But the number of parts here is at most n. Is that okay? Good, right? If we put this column and just merge it on the side, would I lose that vague triangular shape that partitions have? Would it still be a partition? If I were to just add them together, just put them together, here's your box, and then here's that vague shape. This is still a partition, right? Cool. And it has exactly n parts. Like this guy never goes down. Like this, it's most n parts. So I put them. I know that this merging is a partition that has exactly n parts. So what did we learn? We learned that this product Qn divided by QQn, Q base Q sub n, is giving me partitions into exactly n parts. So this alone, the sum and alone, is the generating function for partitions into exactly n parts. So I have the generating function for all the partitions into exactly n parts. Because to give me a partition into n parts, I would just take the first column, that is my Qn, and the rest, that is any partition that is coming from here, right? Now, I want to sum it up over n. Now, this is the portion that I have discussed. I want to sum it over all n. What am I doing? I'm summing over n. It means I'm adding the generating function for partitions into exactly 0 parts with all the partitions into exactly 1 part, all the partitions into exactly 2 parts, all the partitions with exactly 3 parts, and so on and so forth. So the sum, once I do that, this is the generating function for the partitions or for the number of partitions. But into exactly n parts, that condition goes away because no matter what n was, I summed over that. I already have it in my sum. Do you want partitions into 50 parts? It is in this sum at n equals 50. Do you want partitions into exactly 100 sums? It is n is equal to 100. So this was the generating function for the number of partitions. This is the generating function for number of partitions. So here's a combinatorial proof. So it is really useful to be able to just manipulate these Ferris diagrams here and there so that you can just give combinatorial proofs of analytic identities. We can include more information, so we know how many parts this guy has. It has exactly n parts, so I might as well put an z to the n to say that z to the n is counting the number of parts, right? The exponent of z is counting the number of parts, and I'm not counting anything extra here, so the total is like z to the n. So this would be q to the n z to the n divided by QQn. That is generating function partitions into exactly n parts, where the exponent of z is counting the number of parts. The number of parts Cool. But then I start summing this up over n. Well, I will still lose this middle thing because it was just saying that that condition is exactly n parts, but I'm summing over all the possible n's. And this extra information stays the same. So this is the generating function for the number of partitions, for the partitions, where z to the n, the exponent of z, where the exponent of z is counting the number of parts. Cool. So we were able to retrack where that z is, right? And here we already solved this in an example that when you want to count the number of parts, you just need to add that z in this product representation. So you see, we proved an equivalent version of the Q exponential theorem, which was an analytic theorem using just combinatorics. These are equivalent, right? Before the z, my results, like the result that we shown here, was a little bit weaker because it didn't have the extra variable in it. But we were also able to put that variable back into the equation. And these are equivalent. Just the equivalence is here you take z to go to zq, and then you're here. Right? Or you take this one, you take z goes to z over q, and you're there. It's fine. And this is an art. This is an art form to be able to write these generating functions in multiple different ways, because every different way of writing this gives us some extra information. Good. Maybe I can do the similar thing for the partitions into distinct parts. So, and this will be quicker. Khan also proved this relation. So z q sub infinity is equal to sum -1 to the n q to the n minus 1 divided by 2 z to the n divided by qn. Another analytic identity, we got it from Q binomial theorem. This one looks like the generating function for the distinct parts, don't you think? If z is negative q infinity is the generating function for the distinct parts. So let's plug that in. Let's try to prove it in the way that we did. So if I were to plug in z equals negative q, I would have minus q sub infinity is equal to, so there's that minus coming in, that negative is going to go out because I'm plugging in negative q, right? So that negative is cancelled. I have n squared plus n divided by 2 and this whole thing divided by q sub n. Again, we will focus on the sum end first. First the sum end, then the sum. So the sum end, q n squared plus n divided by qn, I will do exactly the same thing. I will split it in two pieces. N squared plus n over 2. I have 1 over qn, and I even know how I want to interpret this. This is a partition into at most n parts. Just the same setup. Maybe it has n parts, but most likely less. What about the first part? So this is the generating function for the partitions into distinct parts. I don't have that condition of things being distinct on the second half. That condition should come from the first half. When I put them together, I will make sure that it's a partition into distinct parts. And look at this guy again. This is a triangular number. So n squared plus n over 2 is the sum of 1 plus 2 plus 3 all the way to n. So I have n numbers. The sum of the first n numbers is n squared plus n over 2. So in pairs diagrams, this is representing the partition of 1 to all the way n, but I would have written it like the reverse way, n minus 1, so on and so forth. So this is the pairs diagram where we have This is the Ferris diagram of n minus 1, n minus 2, all the way to 1. So this is the triangle which is into distinct parts with exactly n rows. So it is a triangle with exactly n parts. This guy has distinct parts. So the first part was like the smallest one is 1, the second smallest is 2, 3. This has distinct parts. This might not have distinct parts. But if I were to put them together row by row, the outcome would have distinct parts. Because these already differ by 1. If they don't differ by 1, because of that sum, it will differ by at least 1. Right? So put together, you get a partition into exactly n parts, and that partition is distinct. Now, however, there are considerations that we need to make right now. We need to say, is this a bijection? Like, am I just mixing up things and overcounting things? So can two sources create the same partition twice? Because that's not what I want to do. I want to count every partition just one time. I want to take a partition and count it just one time, right? So if I were to do this combination of two different things, can it ever create the same partition from two different sources? So can I have a different n and some secondary partition and make the same partition? Well, I'm going to say we can't. We are directly controlling the number of parts, exact number of parts. So if you're given a distinct partition, look at the number of parts. You already know what triangle you have on the inside. When you pull it out, you get the other triangle. So this is a reversible thing. This is a bijection. Okay? Given any partition, look at the number of parts, take the triangle, you directly make up your q to the n squared plus n over 2 portion. Whatever is left is coming from the 1 over qq sub n. So this is, now we recovered that this is the generating function for partitions into distinct parts into distinct parts, where we have exactly n distinct parts into distinct parts with exactly n parts. So when n is 50, I'm counting the partitions in distinct parts into exactly 50 distinct parts. When n is 51, I'm counting them into exactly 51 parts. So when I sum it over all possibilities of n, I'm just counting the number of partitions into distinct parts. So this condition just goes away because I'm summing over all of the possible number of parts. Cool. So this is then the generating function for the number of partitions into distinct parts. Distinct parts. Well, great. We learned it from this construction, but we also knew it from the other side. This was already shown to us that this is the generating function for the number of partitions into distinct parts as well. So we have that connection again. And once again, this is a little bit weaker than the original theorem. This has a z, this doesn't have a z right now. Can we include that z? I think we can. Again, this z here is counting the number of parts, right? If I were to add that, this should be over to zn. That will be counting the number of parts. So I have one z for every row, in a sense. And if I were to add that zn, that would be counting that. And here we already saw that the number of parts will be counted by z in the first argument. Now, okay, in the last 4 minutes, the point is, yeah, this is an art. This is a really art form that you write generating functions. You find generating functions so you can play with them. You have a formula. Then the art form is you write the generating function in a different way. And we have like really good artists in this classroom. Like, I mean, we have Khan, we have Jehan, we have Halime. We have really good artists in this classroom. So, but this is a really some sort of an art that you can write the generating function and you can write it in different ways because every one of them have a different flavor. Every one of them give you some more information. I want to mention another artist. And this is a student of Richard Stanley. So Silan Boulay is the artist that I want to mention. And in 2006, Silan Boulay said, you know what, maybe we don't need Q to the size. Because that was the point, right? Maybe we can do something more general. So maybe when we're given a Ferris diagram, like the 1, 2, 3, 4, 4, 3, 2, whatever that is, maybe we don't need to fill that in with Q's and look at the size of that as the multiplication of the Q's. Why don't we look for a fancier version of this? Why don't we look for a more general version of that? And they defined a coloring of Ferris diagrams. So let's draw a large Ferris diagram and then color it in the way that they did. So if I were to fill them with Q's, then collect the number of Q's, that would be going towards the ordinary generating functions. What they did is, in the odd index row, starting from the top row, you start coloring them as alternating A's and B's. So AB, 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 AB. In the even index rows, you color them as CB, CD, 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 C. Then you repeat. So AB, 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 A, CD, CD, C, AB, A, and C. Cool, great. Then, well, this generating function with just Q's became messier. So we had the generating function for partitions from the set P, all the generating functions into partitions, and we were counting the number of the size. Now that switched to the sum of all the partitions in P, where I'm instead counting a different thing. I'm counting the A to the number of A's in the colored Ferris diagram. Colored Ferris diagram. Long. I will just erase it. So it is just, you count the number of total A's times number of total B's, number of total C's, number of total D's. Okay, right? It's just a construction, more general than what we have done before. And so far, it's an idea. However, what makes it really impressive is she also found the formulas for these generating functions. And you can play a lot with them. You can just do a lot with them. So if you were to look at these pies, P with the weights that we're talking about, say B, C, and D, she said, this has a formula, and it looks like this. Minus A base A, B, C, D sub infinity. It is an infinite product. Minus A, B, C base A, B, C, D. And on the bottom I have three pieces, so A, B, base A, B, C, D. AC base A, B, C, D. And A, B, C, D base A, B, C, D. Infinity. So she found the formula for this guy, which is a beast of a thing. It is much more general than like what we were playing with, and it was already hard to some extent. And she also found the generating function for this thing parts with these weights, and it's similar. That is, the top factors are the same, A, B, C, D, minus A, B, C, A, B, C, D. And on the bottom, I will have just AB, base A, B, C, D. So one thing to check now is, for example, plug in A being Q, B being Q, C being Q, D being Q. Is it going to go back to the original generating functions that we looked at? It will, but play with it at your time, at your own time. We can do it like in the beginning of the next lecture as well. And it's almost like it creates a lot of opportunities. It is just I mean, a 4-variable generalization of something that was giving us quite some information about partitions. Now we have 4 new dimensions open up instead of Q. And yeah, that's where I want to leave you for today. Leave you with today. So this is the main theorem of Sillan-Boulay from 2006. And then we'll go to newer results. Right, thank you. Do you have any questions?